Hello everyone, welcome to my channel. Today I'll talk about cell momentum balance. Here I'll discuss velocity profile development for flow through an annulus. Now here is the problem statement. So derive the velocity profile for a steady laminar flow of an incompressible Newtonian fluid through a vertical annulus using cell momentum balance approach. Now in the right hand side you will see here two concentric pipes, and in the annular phase fluid is flowing. So now here we have to find the momentum flux distribution tau rz, that is function of r, velocity profile vz, that is function of r, location of maximum velocity, relationship between flow rate and pressure drop. Now here is the system description and physical setup. Now given condition, so geometry vertical annulus space between two concentric cylinder. Now here is the one cylinder, another is the large cylinder. So inside one small cylinder is there, and outer, that is the large cylinder. So outer cylinder radius is r. So you can see that this is the central line, and the radius, the big cylinder is r. That big cylinder radius is capital R. Inner cylinder radius is kr or kappa r, where that k is 0 to 1. And fluid here is the incompressible Newtonian fluid with viscosity mu and density rho. And flow is steady, laminar, and it is upward in z direction, means flow is flowing in the upward direction, this direction. And driving force here, pressure gradient and gravity. Now that annular flow system, so annular phase means space between two concentric cylinder. I already talked about that. And outer cylinder radius is capital R, inner cylinder radius is that kr, where k less than 1. And flow direction upwards means positive z direction. And coordinate system is, that is, as it is a cylindrical, so r theta z system. Now here actually k is the ratio of inner to outer radius. And lambda is the parameter defining the location of maximum velocity, that we will find out. And velocity varies with radial position only. Vz is equal to Vz of r. We will come details. Now here is the fundamental assumption. So standard transport assumption. So we are considering that it is a steady state flow. So dou by dou t, dou of something by dou t is equal to 0, because it is a steady state flow, means something change with respect to time is 0. An incompressible fluid means rho is constant, and it is a unidirectional flow. So no other direction there is, means no flow in other direction. So that's why it is unidirectional flow. Only Vz component is significant. So V theta is 0 and Vr, that is 0, means velocity in theta direction is 0, velocity of r direction is 0. Only Vz component is significant. No slip condition at solid liquid interface, Vz is 0. And significant gravity effect, so rho g term should be included. Now here is the special assumption for annulus. So maximum velocity location. Now you can see here. So maximum velocity here. Okay, so that maximum velocity location. So Vmax occurs at distance lambda into r from the center. So now here, if we consider, so from the center to here, so that is lambda r. So there will be the maximum velocity. So remember, this is not necessary at the geometric center of the annulus. That means it is not like that this lines at the line should be at the center of that annulus, means here this wall and this wall, it will not always in the middle. Okay, so that's why it is, this is not necessary at the geometric center of the annulus. At r is equal to lambda r, means r is equal to lambda r, that Vz is actually maximum, Vz is maximum, and Vz by dr, that is 0. So 0 momentum flux. Now step 6, write momentum balance. So for a system under steady state condition, the principle of momentum conservation is expressed as follows: rate of momentum inflow minus rate of momentum outflow plus net external force on the system is equal to 0. So that is the momentum conservation equation. So momentum is transported in the system through two primary mechanisms. One is molecular transport due to shear stress known as a viscous transport. Another is convective transport due to the collective movement of the fluid as known as bulk flow. The external forces considered in this balance typically included surface force, which result from the pressure exerted on the system's boundaries. Another is body force such as gravity, which act upon the entire volume of the system. So now here this flow is pressure and that gravity driven flow. So we have to consider pressure and gravity. So that's why body force such as gravity which act upon the entire volume of the system, we have to consider that. Now cell momentum balance general form. So I already talked about that. Rate of momentum inflow minus rate of momentum outflow plus net external force on the system is equal to 0. As it is a steady state, so that accumulation term is 0. So rate of momentum in minus rate of momentum out plus force is equal to 0. Now here momentum transport mechanism. So one is molecular transport. So viscous momentum flux, that is tau I rz. Another is pressure force, that P acting on the surface, and gravity force, that is acting whole body. And here we are considering full developed flow, so convective transport will be 0. Okay. So now here that cell selection and momentum flux analysis. Now here this is our cell. Okay. So that is a cylindrical cell, radius r and thickness del r. So this is del r thickness and length is r, and radius is from here center line to here, so that is r. Now inner surface area, that is 2 pi r into L, and outer surface area, that is 2 pi r plus del r. Okay, so that is inner and this is outer, so 2 pi r plus del r L. So here this is r and this is r plus del r. So inner surface, that is 2 pi rl, outer surface 2 pi r plus del r into L, and cross sectional area, so that is 2 pi r into del r. So that is the cross sectional area. Now momentum flux notation. So here that tau rz, that momentum is acting. So what is tau rz? So that act at r is equal to r, that is tau rz. So tau rz means flux of z momentum in positive r direction. So that z momentum, because flow is happening in the z direction, so that will be z momentum we have to consider in positive r direction. So positive r direction, that is tau rz. Another is r plus del r. So same momentum will act r plus del r. So now, and pressure force also acting on the cell, that is at 0, z is equal to 0, so there is a p0, and z is equal to L, that is pl. So that is at z equal to 0, pz 0 into, so force you have to multiply it with 2 pi r into that del r. So that cross section into pressure, so that will give the force, that is upward force. Another is z at L, so that pz, z is equal to L into 2 pi r dr, so that is downward force. So net pressure force will be pz at 0 minus pz at L into 2 pi r dr. Now momentum flux, so already we know, so that is the momentum flux tau rz acting at r is equal to r and r plus del r. So that is tau rz into r into 2 pi rl. So it will act on the inner surface. Okay, so that is tau rz at r, that is 2 pi rl inward, and outer surface tau rz. Okay, so here if you see the ring, okay, so inner surface, another is outer surface. So that is outer surface 2 rz r plus del r, that is 2 pi r plus del r into L in the outward, and weight of the fluid is rho g into volume. So that is volume is 2 pi r del r into L into rho g, so that will be minus rho g because gravity is acting in downward direction. So rho g into 2 pi r del r into L. So now we have all momentum plus all forces. So now we have to together. So all terms combine. So P 2 pi r del r z is equal to 0 minus 2, so pi into 2 pi r del r z in, as L, plus tau rj 2 pi rl at r minus tau rj 2 pi r plus del r into l at r plus del r, and then minus rho g 2 pi r del r l is 0. Now dividing by 2 pi r, 2 pi r l del 2 pi l and del r, so we will get p at z is equal to 0 minus p z is equal to l by l r plus tau r z into r at r minus tau r z r at r plus del r by the del r minus p, sorry, rho g r is equal to 0. Now if I take that limit del r tends to 0, so we'll get the derivative term, and then p0 minus pl by l r minus d by dr tau r z r minus rho g r. Now here, so rearranging the cell balance, so we will get that. Now if I rearrange like that, okay, so dy tau r z r by dr p0 minus pl l minus rho g r. Now here let p0 is p0 rho g at 0, p that is p0, and pl minus rho g l, so we can write like that. So p0 minus pl by l minus rho g, that is p0 cap minus p0 cap l by l. So we plug that. Okay, now we have to do the integration. If I do the integration, so finally from here to here, and then we will get this tau rz r p0 minus pl by 2l r square plus c1. So c1 is constant. Now here again, that after rearranging, so we'll get tau rz is equal to p0 cap minus pl by 2l plus c1 by r. Now here boundary condition for c1 at r is equal to lambda r, so location of maximum velocity, so tau rz is equal to 0. So now here tau rz 0, so from that we get c1 is nothing but minus p0 cap minus pl cap by 2l lambda r whole square. Now if I plug the tau rz, so we'll get the big equation. So p0 cap minus pl cap by 2l into r minus p0 cap, this is the c1 term, minus 2l, the lambda r square by small r. Now if I factoring, so that will give tau rz is equal to p0 cap minus pl cap 2l r minus lambda r square by r. Now from here if we take the lambda common, so we'll get this equation. So tau rz is equal to p0 cap minus pl cap capital R by 2l in bracket r by capital R minus lambda square r by small r. Now this is the momentum flux expression. So now tau rz is equal to 0 at r is equal to lambda r. Okay, so that will be maximum velocity location, and tau rz changes sign across the that annulus. Momentum flux distribution depends on lambda parameter. Now from here we put the Newton law of viscosity, so tau rz is equal to minus mu dvz by dr, so we plug that here, and then we get dvz by dr is this whole term. So now again we have to do the integration. Okay, if I do the integration, so vz will be minus p0 cap minus pl cap by 2 mu l r square by 2 minus lambda square r square ln r plus c2. So if you do the integration, you will get this term. First you have to do the integration, then you have to do this integration and plus c2. Now finding c2, you have to put the boundary condition. So first we have to rearrange that. So after rearrange and factorizing, so we'll get vz is equal to this expression. So now after that we put that two boundary condition. So here at r is equal to, because why two boundary condition, so because we don't know lambda, another is we don't know c2. So okay, so for at r is equal to kr, that is vz is equal to 0 because inner surface, and r is equal to capital R. If you see here this figure here, so velocity here also 0 and here also 0, similarly here also 0 and this surface also 0. So you have to take that two boundary condition, and from this two boundary condition we will get two unknowns. Okay, so here that r is equal to kappa r, vz is equal to 0, so inner cylinder surface at, and another is that r is equal to, here r is equal to capital R, Vz is equal to 0. So outer cylinder surface. So now from this boundary condition 1, if I plug R is equal to copper, so Vz is equal to 0. So we'll get C2. So C2 will be P0 cap minus PL cap R capital R square by 4 mu L, and then K square minus 2 lambda square ln K. Another is here that boundary condition 2, R is equal to capital R, Vz is equal to 0. So from here we'll get C2. C2 is P0 cap minus PL R square by 4 mu L. So we'll get that two equation. Means C2 is equal to one form, another here also another form. Now from that, if equating two expression, so from here we'll get that another that this term will be cancel out, r square cancel out, this will be cancel out. So 1 minus that k square minus 2 lambda square ln k. So now from here we can get lambda square. So now since that k less than 1, we have ln k less than 0. So making lambda square positive are expected. Okay, so we'll get the lambda square. Now if we plug that means complete velocity profile, will get that Vz is equal to P0 minus PL cap R square by 4 mu L R square by small r square by capital R square minus 2 lambda square ln R by capital R minus 1. So you can express also in terms of k square. Okay, so you can plug that. You already know that lambda square is this. We can plug that. So we'll get in terms of that case. Okay, so now this is the velocity profile. So here from this the equation we can say that it is a logarithmic velocity parabolic profile combination of r square and ln r in term. Maximum velocity will get r is equal to lambda, and zero velocity both cylinder surface r is equal to kr and r is equal to capital R, and flow rate is proportional to p0 minus pl cap. Now here, so key result, so momentum flux, so tau rz, so that is p0 cap minus pl cap into r 2l, and then r by capital R minus lambda square r by r, and lambda parameter lambda that square is equal to k square minus 1 2 ln k, and velocity profile parabolic logarithmic distribution. And what is the application of this problem? Heat exchanger, oil drilling, chemical reactor, and piping system. That's it. Thank you.